All right, let's go ahead and do this practice exam 5 key. Starts with a question that says, to make a pizza, you require 1 round of dough, 2 cups of cheese, and 3 scoops of sauce. It says, if you go to the store, you buy 5 rounds of dough, 6 cups of cheese, and 12 scoops of sauce. Which is a limiting ingredient? In other words, kind of like how many pizzas can you make? So if I were to make this a chemical reaction, essentially this is saying 1 dough plus 2 cheese plus 3 sauce yields a pizza. And so I'm given these ingredients, I'm given 5 doughs, 6 cheeses, and 3 sauces. And so what you do, you have to keep in mind for every 5 of these, you require 6 of these and 12 of these to make a pizza. So essentially we look at these coefficients and we take the amounts that we have, and you take the amounts that you have and divide them by the coefficient. So I'll divide that by 1, and that will give me 5. I divide 6 by 2, and that gives me 3. And I divide sauce by 3, and that gives me 4. So which one is smaller, 5, 3, or 4? This one's smaller. And that is why my 2 cups of cheese is my limiting reactant. Now you could have drawn this all out and taken a while, but yeah, hopefully that makes some sense. In a balanced reaction where 5 mole of lithium reacts with aluminum fluoride, how many moles of aluminum fluoride are required to react? So in this reaction, lithium and aluminum fluoride will form lithium fluoride and aluminum. We should recognize this as a single displacement reaction. Now we have to balance it, because over here I see that there's 3 fluorides, so we need 3 there. That changed the amount of lithium, so we need 3 lithium. We have 1 aluminum and 1 aluminum, and that looks relatively balanced. So let's go through this again. It says where 5 moles of lithium reacts with aluminum fluoride. And then it says how many mole of aluminum fluoride are required to fully react. Well, in this case, we're looking for this one. So we say 5.0 mole of lithium goes here. If this is lithium, we have to put mole of lithium here. We know for every 3 mole of lithium, we require 1 mole of aluminum fluoride. And that's why it's really important that we balance this reaction and we understand what everything is. Those cancel. 5 divided by 3, we'll get 1.66, or B as the answer. Okay, and the next question, it says, how many mole are in 12 grams of F2? Well, the first thing we do when we see grams is what? Turn it into moles. You turn it into moles by dividing by molar mass. It's something we learned at the beginning of the semester, and we should be doing it like this by now. So I say, okay, we got 12 grams of F2. To turn grams into moles, you divide by the molar mass. If this is grams, we have to put grams here. Now, if looking on a periodic table, here I've got fluorine is 19 grams per mole, but this isn't fluorine, this is F2, so it's 2 of them, so that's 38 grams in a mole. So I can look at this already and say, hey, that's about a third. It's going to probably be D as an answer, but nevertheless, I'm doing this with you guys, so I'm going to calculate it. 12 divided by 38, and sure enough, it equals 0.32, or D as my answer. All right, and number 4, it says, given the following reaction of 12 grams of F2, hey, check it out. We already know that 12 grams of F2 is and I'm going to use some extra sig figs, 0.3158 from the previous problem, mole, because we should always turn grams into mole. It says how many grams of solid was produced? Well, where's the solid that's being produced? That's over here. These are the things that are going to be produced. So we're going from here. So essentially we're starting with 0.3158 mole, and we're going over here. At this point in your stoichiometry career, you should be able to take this number divided by 3 and multiply it by 2 quickly. If you're not doing that, that's okay. Let's go ahead and draw it out so that you can practice and get that fast. But by the time you come to take an exam, you shouldn't be writing this out. You should just be going from here to there to there to there. So 3.158 mole of F2. I know for every 3 mole of F2, there's going to be 2 mole of this solid that's produced, which looks like it's chromium 3 fluoride. But that's not where we're stopping. It asks for grams, and you're given the mass to save you some time. So we know that a mole of CrF3 has 108.99 grams. So we're going to take the number of moles we have times 2 times 108.99 divided by 3, and I get an answer of 22.94 grams, or C. Moving on to the next question. It says when 1 mole of aluminum oxide reacts with 2.5 mole of sulfuric acid. So right away, when I'm given moles in some kind of reaction, I like to write what I got down. 1.0 mole of aluminum oxide is reacting with 2.5 sulfuric acid. It says, what is the limiting reactant? Well, just like we did with the pizza example, you take the amount that you're given and you divide by the coefficient. So I'm going to divide that by 1. I'm going to divide that by 3 to find out which one you're going to run out of first. This would give me an answer of 1. This could give me an answer of less than 1. I don't even need to do the math. I can tell that sulfuric acid is my limiting ingredient. All right, number 6, it says when 1 mole of aluminum oxide, 1.0, reacts with 2.5, how many grams of aluminum sulfate can be produced? In other words, a theoretical yield. So essentially this question led you into this question. We already know that sulfuric acid is a limiting ingredient or a limiting reactant. Now we can take that number, 2.5 mole of H2SO4, and it's asking for aluminum sulfate. So we're trying to get over here, but in grams. So we start with sulfuric acid. We know for every 3 mole of H2SO4, you get 1 mole of the aluminum sulfate, Al2SO4 3. Again, we're in mole town of aluminum sulfate, but we have to get to gram town. We know that in a mole of it, you're given the molar mass, there's 342.15 grams. Okay, so now I'm going to take 2.5 times 342.15 divided by 3, and I get an answer of 285, which would be 2.9 E2 with 2 sig figs. So be careful. It's easy to look at this and be like, 285 grams, that answer's not on here, but it sure enough is. 285 would be 2.85 E2, right? But with 2 sig figs, that would be 2.9 E2. So don't forget your sig fig rules and putting things in scientific notation. Okay, when 15 grams of calcium bromide, what do we do with grams? Turn it into moles. Calcium bromide, you should know that calcium is a 2+ charge, bromide has -1 charge, so calcium bromide is CaBr2. If I figure out the molar mass of calcium bromide, because it's not given to you, the molar mass of calcium is 40.08 plus 2 times the bromide, which is 79.90. And each of these are in grams per mole. So I'm going to say 2 times 79.9 plus 40.08. And I get an answer of 199.88 grams per mole. So now I can take that 15 and divide it by 199.88 grams per mole. And that will tell me how many moles of calcium bromide we have. And then we can start reading the problem. So 15 divided by. That answer gives me 0.075 mole. Okay, so now we have that number of mole. And so essentially I would just kind of like cross that out and say that this is actually 0.07504 mole. It would have 2 sig figs. And then it says, so when that much is dissolved in 0.2 liters of water, what is the resulting concentration in mole per liter? Ooh, that makes it easy because remember, big M is mole per liter. I said it already, but I should have just written mole per liter. That's what we do when we got a big M. And so the question is, hey, how many moles are in a liter? Do we know how many moles are in there? Yeah, there's 0.07504. We did that because we just always turn grams into moles. Do we know the volume? Yeah, it's 0.20 liters. So essentially we're taking 0.07504 mole, and we're gonna go ahead and divide that by 0.20 liters. And you get an answer of 0.375 mole per liter, which would be 0.38 with 2 sig figs. Okay, I got a toy crisis sorted out with my kiddos and back on track. So it says when 4.7% of a 1.1 mole per liter solution is poured into a beaker, what is the concentration of the solution in the beaker? This isn't something we went over. And so, well, we went over it, but we didn't talk about anything to do with percents, etc. And so, let me go ahead and pull this up because there's an additional answer right here. But we did say, hey, anytime you take any kind of solution and pour it into a beaker, the concentration is still the same. It's like if you took 100 proof vodka and a big bottle of 100 proof vodka and you poured it into a little container, that's still 100 proof vodka. It didn't change the fact that it's 100 proof. So this 4.7 of 1.1 mole per liter solution, the concentration is still going to be 1.1 mole per liter. Again, you take something, you pour it into another container, it doesn't change that fact at all. And we discussed that when we talked about donuts in an earlier lecture. All right. Question number 9. What volume of a 1.4 mole per liter solution contains 74 grams of HCl? 74 grams of HCl. We see grams, we immediately put that into moles by dividing by molar mass. So I'm going to take 74 divided by 36.46, and I get an answer of 2.03 mole. And it says, now what volume is 1.4, big M is mole per liter. Solution contains this many mole. Now we're not worried about grams, we've got mole. So essentially we've got 2.03 mole of HCl. We know that there are 1.4 mole of HCl in a liter. And this would give us an answer of volume. So I take 2.02 divided by 1.4, and I get an answer of 1.45, or 1.4497. So that's why 1.4 with 2 sig figs would be our answer. Moving on to number 10. After dilution, a solution's concentration is bleh. Then after dilution, that makes 0 sense whatsoever. Let's go ahead. I probably at one point, this is an old exam, let's go ahead and change one of these. Let's say before dilution. So if you say before dilution, the solution's concentration is bleh, then after dilution, the answer is going to be higher, because if you have something like, let's say that's 1.5 mole per liter and you add water, essentially you're going to lower that concentration. So before dilution, a solution's concentration is higher than after dilution. All right, number 11, this one is kind of one I've been waiting to get to, because hopefully the video's rubbed off on you and you're like doing this almost automatically. It says when 3.7 of a 1.6 mole per liter solution, hey, 3.7 of a, remember what you do, you multiply those together. So you got liters and mole per liter, you multiply those together and that'll give you moles. So I'm taking 3.7 times 1.6, I get 5.92 mole. So now you got 5.92 mole, and it's diluted to a volume of 6.0 liters. What is the resulting concentration? Well, concentration is in mole per liter, so we're going to take 5.92 mole and simply divide it by the 6.0 liters. So I get an answer of 0.99. So D is my answer. All right. Moving on to number 12, when 45 milliliters of a 0.85. Hey, remember we gotta change milliliters into liters by moving the decimal place over 3 times, so 0.045 liters of a, so we're gonna multiply 0.85 mole per liter solution. So I've got 0.045 times 0.85 of beryllium bromide. So when it's telling us that, hey, if beryllium bromide, again, 0.045 times 0.85 gives me an answer of 0.03825 mole, reacts with 0.46 grams of lithium hydroxide, and it gives you the mass of lithium hydroxide. 0.46 grams, we've got to divide it by 23.95 grams per mole, because that's what we do when we got grams, we turn it into moles. 0.46 divided by 23.95 gives me an answer of 0.0192 mole of lithium hydroxide. Okay, so now we've taken care of kind of all that. It says how much product would precipitate now in grams. So this is a reaction that, quite frankly, I shouldn't even have to give you the reaction at this point. You should understand double displacement reactions. You should know solubility rules. When it comes to hydroxide, you should know that that's going to be insoluble. So essentially it's saying, hey, this, how much of this are we going to make? It's a standard theoretical yield question, but it wants it in grams. So in looking at this, the very first thing we do, we divide that by the coefficient of 1 and that by the coefficient of 2 to find out which one's the limiting reactant. Here I take 0.0192 divided by 2. I'm going to go ahead and do it because they're going to be close. 0.009603. I'm going to do this, and then this one is obviously point. I don't know why I thought that was going to be close. I was going backwards. This is definitely going to be smaller. And so if this is smaller, that's our limiting reactant. And now we're going to say, take that amount, 0.0192 mole of lithium hydroxide. You know for every 2 mole of lithium hydroxide, you're going to get 1 mole of the precipitate. How did you know it was a precipitate? Again, because it's the solid thing that's formed, that's what the precipitate is. From chapter 5. And then it asks for grams and it gives you the molar mass. So we know a mole of this stuff has mass of 43.03 grams. So now I'm taking 0.0192. Personally, I like to start back at the beginning. I like to go all the way back to the number I used when I did this. Then I'm going to say times 43.03 divided by 2. And that gives me an answer of 0.41. So C is my answer. Equals 0.41 grams. All right, cool. So in other words, you mix this stuff together and you get the most you possibly get. The theoretical yield is 0.41 grams. Question number 13, you react 95 milliliters of 0.85. So what I'm doing automatically, I'm just saying 0.095 liters times 0.85 mole per liter to give me moles right away. 0.095 times 0.85. And I get an answer of, let's make sure this is for silver nitrate, 0.08075 mole. In case you can't read that, I'll put it up here, 0.08075 mole. Solution with 25 milliliters, in other words, 0.025 liters, times 1.1 mole per liter. I get an answer of 0.0275. Mole. It says, what is the limiting reactant? Okay, cool. So essentially you're going to divide that one by 2, divide that one by 1, and ask which one's smaller. So the main objective here was just to see if you could multiply moles and liters together and get the limiting reactant from there. It looks to me like this one's going to be smaller. It's going to be 0.04. This is going to be 0.0275. And so calcium bromide looks like the limiting reactant to me. All right. Now it says you add, I underline it and make it all obvious. You add 195 milliliters, in other words, 0.195 liters of water to a beaker with 0.435 liters of multiply. 0.435 times 3.05, and I get 1.327 mole of silver chloride. It says, what is the concentration of the newly diluted solution? Well, that's really funny because silver chloride is actually insoluble. But this gives me an answer of 1.327 mole. So in other words, what it's saying is, hey, you had 0.435 liters of a solution that had 1.327 moles in it. Then you added to that an additional 0.195 liters. So now you're taking 0.435 and 0.195 to get your total volume. And that gives me an answer of 0.630. Liters. And so it's saying, what's the new concentration? Well, big M is always mole per liter. And essentially you just have to figure out the number of moles in there, then divide it by the total number of liters. We already knew the moles. When you added water, you didn't add any additional moles of silver chloride. So we've got 1.327 mole. And we'll divide it by the 0.630 liters. We know that when we add water, the concentration has to go down, so it couldn't go up. Often a very common answer here would be like the 4.21 or something like that. But it doesn't make sense because you can't increase concentration by adding water. And here I get 2.11. D is my answer. All right. Number 15, a reaction produces 42 grams of carbon dioxide. I give you the mass of carbon dioxide, so we're going to take 42 divided by 44.01, and I get an answer of 0.954 mole. How many grams of oxygen gas must have reacted? Well, it's saying essentially, hey, you've got 0.954 mole of CO2, and you want to know this answer in grams. In order to get this, how did we get this? Again, we know that for every 16 of these, we had to have used up 25. So the answer should be higher, in terms of moles. And then we got to put it in grams. 0.954 mole of CO2. We know for every 16 mole of CO2, we get 25 mole of O2. And we know a mole of O2 has 32.00 grams. Let's go ahead and calculate that out. Times 25 times 32 divided by 16. And I get an answer of 48 grams. Or D as your answer. All right, moving on to the last set of questions. These guys go together. It says, for the next 5 questions, please utilize a reaction where silver nitrate, I'm going to write it up here, where silver nitrate, AgNO3, reacts with calcium bromide. Hey, we already did that, Br2. If you remember, the mass was like 199.88 grams per mole. Hey, look, it's right there. And it says reacts in a precipitation reaction, meaning we're going to get a solid out of this. So silver nitrate and calcium bromide will form silver bromide. and calcium nitrate. Now we have to balance the reaction. Going kind of from left to right, the only point of discrepancy I see is this bromide. So this has 2, so we need 2 over here. That altered the number of silvers. Now we got to put a 2 over there. Now we're looking good. We got 2 nitrates, 1 calcium, 1 calcium. So this is a reaction that happened. The next thing you should be saying is, hey, what's the solid going to be? Because this is a precipitation reaction, we're probably going to be paying attention to that fact. If you remember, nitrate is always soluble. So in a precipitation reaction, we're pretty much just looking at the products and saying, hey, what's going to be soluble or insoluble? This one's aqueous. That means this one had to be solid. Or you could look up your rules, or you should have memorized your rules that bromide with silver will be insoluble. So this is our precipitate, this silver bromide. Okay, so it says 130 grams of silver nitrate. Let's go ahead and turn all the grams into moles. 130. So I'm going to take this and divide it by 169.87. Divided by 169.87. This gives me an answer of 0.765 mole. Reacts with 42 grams of calcium bromide. Again, that's 199. I guess I rounded down in the last problem, 199.89. So that gives me 0.2101 mole of calcium bromide to form 63 grams of silver bromide. Hey, we're forming. So if you remember, when we start forming stuff, we kind of put stuff down here a little lower. So 63 divided by 187.77. That gives me an answer of 0.3355 mole. Okay, so all these are in moles now. Now we can kind of start reading the problems and reading the questions. It says, which of the following is a limiting reactant? Hey, we know how to do that. You divide that by 2, divide that by 1, ask which one's smaller. Looks to me, if I divide this by 2, that's going to be like 0.3 something. If I divide this by 1, it's going to be 0.2. So calcium bromide is smaller, it's a limiting reactant. This is what is the actual yield in mole of silver bromide. That's how much we actually made. Well, that's pretty convenient because it said we mixed this, and we made that. Hey, our actual yield was 0.34 mole. We already made it. And now it says, what is a theoretical yield? Well, to get theoretical yield, we have to use our limiting reactant up here. We know that our limiting reactant was calcium bromide, so we're going to say, hey, 0.2101 mole of calcium bromide. We know for every 1 mole of calcium bromide, we had to make 2 mole of silver bromide because it's asking for the limiting reactant in mole. So essentially, that looks to me like it's going to be 0.42. No calculator needed yet. Now it says, what's the percent yield of the reaction? Well, this whole problem's kind of been setting you up to figure out the percent yield because you already know your actual yield was this 0.34. You already know your theoretical yield is this. And percent yield is just actual over theoretical times 100. Again, our actual was 0.34 divided by 0.42. And of course, I like to keep extra sig figs in my calculator. I'll be using the numbers that had extra sig figs. Divided by, and then times 100%. And it looks to me like I get 80%, or C. Now this next one says, what mass of silver nitrate remains unreacted? So this is the one that really separates those who understand what's going on versus those who are following a process. So let's help you understand. I'm actually going to spend a little bit of time here. I'm going to rewrite this problem to AgNO3 plus calcium bromide, yielding 2 silver bromide That's our solid. And calcium nitrate. It said we start it with 0.765 mole of silver nitrate and 0.2101 mole of this. And it says, hey, you made 0.3355 mole of silver bromide. Well, we know that we didn't get 100% yield. We only made about 80% of what we should have made. That means we didn't use up all of this stuff. Not only that, this is the excess reactant. We should have had excess of it. But can we figure out, if we made 0.335, can we figure out how many moles of this we had to use up? And we totally can, because for every 2 moles of silver bromide, you had to use up 2 moles of silver nitrate, telling you immediately, you know, that this is a 1-to-1 ratio. If it weren't, we could just figure it out using stoichiometry, but essentially, we used up. We had to use up this much to make that much over there. And now, it's a matter of simply subtracting our 0.765 minus 0.3355. And I get an answer of 0.425 mole. So in other words, in order to make this amount of silver bromide, we had to use up that much silver nitrate. But we didn't use up all the silver nitrate. There was extra stuff left over. It's like if we go to make the pizza in the very first problem, we had some extra sauce left over, and we also had some extra dough left over, right? And so the same situation applies. So we know we have that many moles. The question is, how many grams, though, is that? So we know that a mole of silver nitrate has a mass, according to the information you're given, of 169.87 grams. So just go ahead and multiply that by. And I get an answer of 73 grams, and that's why that is my answer. So this, I really like this question because it really shows whether or not you understand conceptually what's going on, and the rest of them, hopefully that gives you a good idea. This was a full-on exam from last semester, so hopefully it gives you a good idea of what I expect you guys to know and the pace I expect you guys to be able to do it at. All right, y'all, have a great night.